Okay, somebody, maybe I'll go ask someone. Okay. นัทกมลนะคะ นัทกมล could you please explain the slide that I maybe sorry maybe let me spend just a minute to write down your name. Okay, Nakamon, huh? Nakamon, could you please help explain what you understand about this slide?
ครับ the process variability is can.
Okay, could you please make your voice louder?
Okay. Okay. So this in this slide it tells about the type of process variability, which can be into three types. The first one is stationary, which is independent. There's a fixed mean and a stationary mean that will not various is independent with period data point. And next one is autocorrelate, which is dependent with period data point and it has trend. And the last one is non-stationary, which it drift without any sense and cannot predict what trend or the next point will be at.
Okay. You understand correctly about the first process. Okay, but the second process actually that is like short-term trend. You can say trend or actually we do not say call it trend. We call it autocorrelation. Okay, within short term. Okay, let me see. Okay, let me get a pen first. Okay, if we talk about trend, so usually we mean like long-term trend. Like in this picture, there is a long-term trend, which is the trend down. But in this case, there's no trend. Like in short-term trend, long-term trend is stationary. There's no trend. But there's other correlation in short term, like during this short period. Okay, there's other correlation or a dependence among the data. Okay, and okay, and for the control charts that we will learn in this course, so it deals with which type of process, A, B, or C?
A.
Yes. Okay. So let's move to this roadmap. Okay. So process type A. Now, let me get a pen. Okay. Type A. Okay. Deal with no autocorrelation. Okay. No autocorrelation. Okay. So. But if there's autocorrelation, we will use the technique, which is like engineering controller, or we can call EPC, engineering process control. Okay, and or fixed time series model. Okay, time series model is the equation for forecasting the next data based on previous data, which involve seasonal or trend. Okay. Okay, so in this class we will deal with no autocorrelation, and then Noparat, could you please explain, okay, how do we select types control charts? Okay, start from this box. What do you understand about this? Okay, and we have the wording shift size. Do you understand what does it mean? Okay, let's try to explain. Okay, Noparat ka? So I'm sorry, Norapat ka. So sorry, Norapat. Norapat, are you there?
ครับอาจารย์
ค่ะ
เอารถแมพเลยเหรอครับ
ใช่ลองพูดไปก่อน okay let's for only variable okay this tree
อันไหนบ้างนะครับ
อันนี้ค่ะ ด้านนี้ค่ะ เห็นไหมที่อาจารย์เขียนอยู่
ครับ so first we have to check that in order to construct a control chart we have to check that the data is auto-correlated or not so if it is not auto-correlated we have to check that it is variable or attribute and next if
okay and before that what could you please briefly explain the difference between variables and attributes?
Variable is the data type that is called as a number.
Yeah, right. Number actually attribute.
In a quantity,
okay.
and the attribute is the quantity side.
Okay. Okay, that's right. Okay, attribute may be like have flash, have defect, or no defect. Okay, variable mean numbers, real numbers. Okay. Next, please.
So if it is variable, we have to check for the sample size that is equal to 1 or greater than 1.
Ha. Actually, who designed the sample size? Okay. In which case that we need or we will get sample size greater than 1, in which case we should get sample size equal to 1. Remember that?
No.
You don't know, right?
Yes.
Okay, how about, okay, so other people, can anyone answer me, okay, in which situation that we should collect more than one part, okay, per subgroup? Remember from last time we talked about, okay, control chart is a plot over time, so we have to collect the data, okay, for example, every hour or every 2 hours, it depends, okay, on the stability of the process. Okay, for example, if we collect the data every hour, okay, and the number of parts that we collect within each hour is called sample size. For example, I collect 5 parts from 60 parts that have been produced during the first hour. Okay, 60 parts is the population, right? And 5 parts that I collect is called sample, or we can call it subgroup. Okay, and 5 is what we call sample size or subgroup size. Okay, and in which case that we should design to collect more than one piece or one part, okay, per hour, in which case we should collect only one part or one time per hour. Can anybody answer me about this? Okay. Okay, we will revisit this. Okay, maybe I will leave this for a while. Okay, after we learn more. Okay, in this class. Okay, we will come back to be sure that you can differentiate. Okay, between several situations, and then you can select proper types of control chart later. Okay. Okay, these are the types of control charts that we will learn in this course. We will learn only 3 types: X bar with R charts, X bar with H charts, and I with MR charts for variable data. And for attribute data charts, we will learn these 4 types of charts. Okay. The objective for control charts. Okay. I think this is pretty easy so that you can read and understand this, right? It will signal when to adjust the process when there's abnormality happen. Okay, and the benefit is to prevent defects, improve productivities. Okay, and then we can make necessary adjustments. Okay, now let's talk about the concept of control charts. Last time we talked about the types of variation in the process. So now, Parik, could you please explain what is the difference between common cause variation and spatial cause variation?
For the common cause is about the variation that we cannot unavoid. It can happen in any time. For the spatial cause variation, it is about the abnormality or error that happen to the process.
Okay, that's good. Okay. And Pawat, could you please explain, okay, about the action? Okay, who is responsible for taking care of reduction of common cause variation?
So the common cause,
Could you make place your voice louder, please?
Hello,
Huh.
So the common cause, the supervisor will have to be in charge of like a manager to control the supervisor to do the training or instruction to decrease the defection in the working process.
Reduce the difference among people, right? A difference among for each time that they do the jobs. Okay, if the work instruction is more rigid, okay, it's clearer, so everyone will do the same thing, and then it can reduce the variation that is caused by the system, right? Okay, that's good. And how about the spatial cause variation? Okay, who should take care of this types of variation? And you could you please give an example of the spatial cause?
For the spatial cause, like the mechanic or like the technician have to working with the machine to do the maintenance to prevent the errors with the broken into a machine.
Okay, that's good. Okay. Okay. Thank you. So let's move to other slides. Okay. Okay. So Pawit, could you please explain the key points of this slide? Okay.
ครับ
ค่ะ What does it mean by in control process and out of control process?
The in control process mean variation are stable, but the out of control mean the variation are not stable in the graph.
And then if the mean of the process is not stable, okay, like in the right hand side picture, right? So how this abnormality, okay, express or happen in the control charts, and which type of control charts that this abnormality will appear. We have X-bar charts and range charts, right? Okay.
Yeah.
If the mean shift up, for example, the mean shift up, okay, where does this abnormality appear? Okay, take a look at the picture.
Okay.
Around 10 and 11 a.m. Okay, do you see the shift, the mean shift?
Yes.
Okay, the mean shift up, right?
Yes.
Okay, and when the mean shift up, when you collect the data from the process that the mean is higher, right, you will get the data which has like high numbers. Is it right?
Yes.
And then if you take an average, okay, of the data, and then you will plot it on which chart, okay? If you want to monitor the mean or the average of the process, right? Okay, you will calculate the statistics, which is called X bar, right?
Yes.
Okay, and next, what will you see, or what you expect to see on the X bar chart?
It should be on a linear graph.
Yeah, which point?
At
You see this?
around 10 to 11 a.m.
Okay, maybe the graph shift a little bit. Okay, if an average move up from this point to this point, right? That's mean, okay, your X bar will move up from, for example, on average at this, at the points within this range to the point which is out of the control limits, like the mean here. When you take an average, your average may be this much, for example, and then if you plot this much X bar onto this chart, you will get like this point, right, which is higher, right? And then we will have the control limit, which is this point we call upper control limits, right? And then if the points that we plot or the X bar that we have got is higher than the upper control limits, what do you conclude about this process? What does it mean? If the X bar at, for example, at 10 a.m., okay, is higher than this upper control limits, what do you think? What do you think is tells you about the process?
The process will out of control.
Yeah, out of control. What does it mean by out of control?
Because the mean variation and even shift up are not stable.
Yeah, but if you take a look at 10 a.m., okay, X bar is higher than upper control limits, but range, okay, is still within the control limits. Okay, so the abnormality happen with the mean or the variation. Variation in this case mean within subgroup variation. Okay, range is the difference between the maximum and the minimum of the 5 parts that we collect from each hour. Okay, so range tells you the difference within the subgroup, right? Because those 5 parts comes from the same subgroup. Okay, so the difference among the 5 parts shows you the variation within the subgroups. Okay, but at this time period, the variation within subgroup, is it normal or abnormal? If
It's
the point, excuse me?
It's abnormal.
Okay, this point, you see the point that I show here. Okay, this point is still within the control limits, right? This point is still within the control limit. If the point is still within the control limits, we can say that the process stays normal. Oh, sorry. Hello. Sorry, I've got some problem with the connection. I'm talking to Supervit, is that right?
ใช่ครับ
Okay, ค่ะ Supervit, let's continue with this. Okay. Actually, when we apply the control charts, we will have the concept that if we allow for some variation that is caused by common cause, right? Okay, and the common cause variation is determined by the width, okay, of the control limits. Okay, so that's mean if the x bar, okay, is within the control limits, so we can say that there's no mean shift, okay, or the mean stay at the same level. Okay, same for our charts. Okay, for example, if this point is within the control limits, so we can say that around 8 a.m. okay to 9 a.m. okay, within that hour, the within subgroup variation is normal, it stay at the same level. There's no change with the within subgroup variation. But for example, at this time period at 10 a.m., x bar is out of the control limits. So we will have to conclude that the mean, okay, within that hour is higher than its normal level. There should be some abnormality happens with the controllable factors, and then we need to find out and correct it. Okay, but at the same time period, okay, this point is within the control limits. That means the range or the variation within subgroup is normal, and then we will believe that there is no change, okay, in the variation within the subgroups. Okay, so x bar tells you about the mean, and the R chart tells you about the within subgroup variation. Okay. Okay. Let me pass this slide. Okay, now let's talk about this slide. Okay, we have talked about this slide, right, from last time. Okay, so Picha, could you please help explain what do you understand about this slide?
This is like the formula to determine the upper control limit and lower control limit.
Okay, could you please louder, please?
ได้ยินไหมคะอาจารย์
ได้ยินค่ะ a little bit louder, please.
ค่ะ These are the formula to determine the upper control limit and lower control limit ค่ะ
Okay, and why the formula should be, or what does it mean by center line equal to mu?
Is the mean of the what do you call that? All the values that we obtain.
Okay, mean from the all data that we have collected, which is the sample or the or is express the mean of the whole population, right? Okay, and why the upper control limit should be at mu plus and minus L sigma? Have I talked about this? Why it should be at z score, okay, z alpha over by 2 and then multiplied with sigma. What does it mean by the multiplication of z and sigma?
I'm actually not sure, but I'll guess that like it is like the allowable variable, like there's like this criteria for quality control that we learned from Ajahn Damrong that use like z-score. So I think it's the same concept that we can allow for some variations for the limit.
Right, that is good. Okay, and then okay, so today we will learn more about this. Okay, what does it mean by z and sigma in this case? Okay, let's move past this slide first. Okay, these two slides just want to show you that this is the exact formula that we will use to calculate the control limits for each type of the charts. Okay, x bar r, we'll use this formula. X bar s, you will see there is a different formula, also x bar r, okay, and NPCU charts, okay, have different formulas, okay, for calculation. But the point is that every formula, for example, the formula for P chart, C charts, x bar r, okay, actually it comes from the same concept, which is this, the concept of this thing. Okay, that's what Pisha have told you about that. The center line is at the mean, okay, of the data, and the upper and lower control limit is at the mean plus and minus some allowable variation. Okay, and the allowable variation, okay, actually is calculated differently from each types of data. For example, if your data is P, which is a proportion and defective, okay, Z divided by sigma, okay, 3 is Z, sigma is this thing, okay, and for C chart, for example, C bar is the mean, okay, of the defect rate, and 3 is the Z score, and then square root Z means sigma for the data, which is defective rate. Okay, so I want to have you know that, okay, for every formula come from the same concept, which is the mean plus and minus some allowable variation. Okay, and now we will talk about the variation. Okay, which is explained by this slide. Okay, if maybe I'll mention about this first. We have learned statistics, right? And then you know the normal distribution, right? And the mean, okay, for example, if they have the mean of the part which is at 10 centimeters, okay, and then we have the sigma, okay, we calculate mean of the process which is at 10, sigma of the process which is at 0.1, for example, and if you take a look at this data, which is 10.1, so we can say that 10.1, which is this is the x-axis. Now, if we take a look at x, which is 10.1, we can say that x is different from the mean, okay, by 0.1. Is that right? And if we compare to sigma value, we will see that this x, okay, this x, okay, is different from the mean, okay. If we compare it with sigma, okay, x minus mu is 0.1, sigma is also 0.1, so this ratio is 1, okay. So we can say that 10.1 is different from the mean, okay, 1 time of sigma. Can you get that? And the number 1 in this case is called z. The z-score is equal to 1. So z-score represents the position of the data that we are considering. Like in this case, we are considering 10.1. So we can say that 10.1 is different from the mean, 1 time of sigma. Okay. And another example, 10.2. Okay. 10.2. So can anybody tell me what is the position of 10.2? Okay, if we express it in terms of the z-score. Okay, z-score means the difference of the x that we are considering compared to the mean, but we do not take a look at only the difference. We will take a look at the difference in terms of the times, the number of times compared to sigma of the process. So can anybody tell me what is the z-score of 10.2?
2.
Okay, great, 2. And how about 9.9? 9.9. What is the z-score of 9.9?
Also 2.
Okay. Actually, it's not 2. The number is 2, but the
Negative 2.
Yeah, that's right. It's negative 2. Let me press this. Okay. Okay, so for every x, we can turn it to z, right? Z, like here I write it down here. So 10 will become 0 for the z axis. 10.1 will become 1. 10.2 will become 2. 9.9 will be minus 1. Okay. 9.8 is minus 2. 10.3 is plus 3, right? 9.7 is minus 3. Okay, and next, okay, this is called standard normal distribution, right? And then you learn this, you're familiar with the z table, right? That is that shows you the probability, right? For example, if I want to know, okay, the probability that the z, okay, score is between minus 3 and plus 3, you can look up from the table, right? And then you can find out that is equal to 0.9973 or 99.73%. And then if you look up for z-score between minus 2 and plus 2 range, okay, the probability will be smaller, is that right? And this is roughly about 0.95 or 95%. Okay, and you should pay attention to this because it will be used, okay, pretty commonly, okay, in statistics and quality field. Okay, and the probability that z-score is between -1 and 1 is 68%. Okay, so we will use this probability, okay, to set up the control limits or to set up the control limit. Let me talk about that first. Okay. Okay. So if this is the fact, okay, we can conclude like this. Okay, so if the mean of the process is at this level, okay, at 10.0, okay, it's the fact that we will have 99.73%, which is very close to 100%, right? Okay, we will have that much probability to see the parts vary within this range, okay, plus and minus 3, right? So we have this much probability to see the point within this range, given that the mean is at this level, right? So, okay, control chart is set up with this concept, and then it will believe, okay, we tend to believe that if we see the point, okay, before moving to that idea, okay, let me introduce you about this idea first. Okay, so this is the distribution of x. Okay, for example, the diameter of the part. Okay, and then it has normal distribution. And if we collect the data in subgroups of 5 parts, okay, per subgroups, and then we calculate x bar, right, from each subgroup. For example, subgroup number 1, okay, we have 5 data points, okay, and then if we take an average, 5 data points may be 1, 2, 3, 4, 5, right, and then we take an average, it will be about this much, okay, and the next subgroup we collect another 5 parts, maybe 1, 2, 3, 4, 5, okay. So the next subgroup, okay, our data tend to be a little bit higher, okay, but given that, okay, if we assume that it still stay at the mean, which is at this level, so there's no mean change, but it just accidentally that we collect the data which is a little bit higher than okay, the first subgroup, okay, so we'll get an average, which is this point, okay, and the next subgroup we may have like 1, 2, 3, 4, 5, okay, the next subgroup we will have the x bar, which is about this much, for example, okay. So now if we take a look at the distribution or the variation of x bar, okay, we will see that the variation will be smaller compared to the variation which the individual data points, right? So it comes to this, okay, distribution, that this is the distribution of x bar, okay, on the average. So we can say that, okay, if we take an average of 5 parts per hour and then take a look at the distribution of x bar, we will see that the mean of the x bar, okay, will be equal to the mean of x. You will see that it shares the same level of mean, okay, but the variation of x bar, if you take a look at the picture, it will be smaller, right? Okay, it will be smaller, and this is what we call central limit theorem that you have learned from statistics course, that the variation of x bar is smaller than the variation of x by this amount, which is divided by, sorry, maybe I'll move to this. Sigma of x bar is equal to sigma of x divided by square root of n. N is sample size in this case. For example, if x sigma is 0.1, and then for each subgroup we collect 5 data points. So sigma of x bar will be smaller by this ratio. If sample size is 9, okay, this is square root 9, okay, which is 0.1 divided by 3, right? So that means if you collect the sample size, which is 9, the variation of the x bar will be 3 times smaller than the variation for x. If your sample size is 4, square root 4 is equal to 2. That means the variation of x bar is smaller than the variation of x by 2 times. So this is the relationship between x bar and x, okay, in terms of the variation. And then when we plot the control charts, okay, we plot keep it, okay, we plot the x bar charts, right? That means the statistic that we plot is an average or x bar. So the control limit, okay, the control limit here is set up, okay, is set up at mean plus 3. 3 in this case is the z-score, okay, and sigma of x bar, okay, sigma of x bar, not sigma x, okay. And the reason that we use 3 in this case is correspond to plus 3 minus 3 is corresponds to this probability that, okay, we allow for almost 100%, okay, of the data to vary, okay. And okay, if this is x bar, okay, and we'll think about this like this, okay, if the mean, okay, is at this level, okay, we expect to see x bar vary within this range, okay, for almost 100%, okay. But if we observe an x bar which is out of the control limit, and then we will place the control limit at this point, okay, this will be upper control limit, this is lower control limits, okay. So if we detect a point which is out of control limit, like this point, okay, so it's unbelievable, okay, that it comes from the process with the mean at this center, okay, because the chance to see the points out of the control limits or out of this fence is very small, okay, because it's only 100% subtract by 99.73, okay, is equal to 0.27%, okay, 0.27% divided by 2 here, and 0.27% divided by 2 here, because, okay, there are 2 sides, so you have to divide, okay, the probability by half, okay. So if we see the point, okay, with just out of the control limit, that we place the control limit on mean minus and plus and minus 3 times of sigma, okay. And so if we detect a point out of the control limit, okay, it can mean 2 things, which shows on the next slide, okay. Okay, this is summarize what I have mentioned before, okay. And 2 ways that the value outside the control limits can mean. The first thing is that extreme value, or that the point which is out of control limit, okay, really come from the process which is in control. But we have to accept that this chance is very small, only 0.27%. Okay, it can come from the process which is at the mean, at the level of mean that is unchanged, okay, or what we call in control process, but the chance is pretty small. Okay, so we tend to believe in the second alternative. That means we tend to believe that value, okay, of x bar, okay, doesn't come from the process that is centered at the specified value or the normal value that we believe, okay, anymore. Okay, but we tend to believe that the average, okay, of the process at that time period, okay, tend to be higher or lower, depends on it out of control on the upper side, on the lower side. Okay, okay, that is the point here. Okay, so we tend to believe that if we see the point which is out of control limit, okay, we will believe that that point is caused by an assignable or special cause or abnormality, something wrong or error. Okay, but at the same time we have to accept that we can conclude wrongly. Okay, that means we can have an error of type 1. That means actually the mean is unchanged. Okay, no change in mean. Okay, but we conclude, okay, that there is a mean shift. Okay, okay, so the fact can be two things. Okay, no mean change and mean change, or what we call mean shift. Okay, no mean shift and mean shift, right? But if in reality the fact is that there is no mean shift, but we conclude that there is mean shift, this is called type 1 error. Okay, and it's possible also, okay, if we place the control limit here and here and the mean is at this level, so but actually this point come from the process which is centered at this mean, right? It's possible, okay, but it has very small chance. So if we place the control limit here and then we conclude that this point is out of control limit, or it explains that there is a mean shift in the process, that's mean we accept this much probability of type 1 error, which is 0.27%. Okay, for both sides. Okay, total. Okay, do you understand the concept that I'm talking about here? Yeah. So at this point, okay, so anybody, maybe I'll random, like Chanin, Chanin. Isari, you haven't answered yet. Isari, okay, up, okay, so far, okay, from this slide, okay, or from the few slides that we have talked about, okay, what do you understand about the relationship between control limits and chance, okay, and the chance of type 1 error? Isari, could you please help explain about this?
ค่ะ
ค่ะ do you clearly understand what okay, what I've talked about previously?
So like if it's fall between the UCL and LCL, it's mean in control.
What does it mean by in control? Could you please clarify it a little bit more? So in control, okay, maybe I'll help you. In control mean like in this case, the mean and the variation stay at the same level like this, okay? If, okay, there's a mean shift, mean things like this. The mean shift up from this level to this level, okay? This is called mean shift up, okay? And the variation shift up mean like this. Mean at the same level, but it's wider. Okay, the dispersion is wider. Okay, this is called variation shift. Variation shift up. Okay, this is, we can say the mean shift up. Okay, and if when we say the process is normal, that means there is no mean shift or variation shift. So that means the process stay at the same level, okay, all the time. That's mean in control, okay. But this means during this time period, the process is out of control in the sense that the mean shift up, and at this time period, the process is also out of control in the sense that the variation shifts up. Okay. And now let's, okay, and if this, the version of x bar, okay, if we see, maybe I erase this first, okay. I'm sorry. Okay. Okay, and if the, think about this, if the mean shift up, okay, up to this point, okay, let's compare the probability that we will detect the x bar here, okay, x bar here, and okay, at the same level, okay, but in this case there is no mean shift. In this case, no mean shift. In this case, there is the mean shift, right? Okay. In which case that is more likely to see x bar at this level? The case of mean shift or no mean shift?
Mean shift.
Yeah, that's right. Okay. So it okay. On the other hand, that means if we detect an x bar here, okay, which is out of control limit because the okay, this is higher than the upper control limits, right? So this point is out of control limits. Okay, so you tend to believe that mean shift or no mean shift if the point is out of control limits.
Can I hear the question again?
Okay, if you see the point or x bar which is out of control limits, okay, if you, for example, if you believe or conclude that the process is in control or stay at the mean at this level, okay, so let's discuss about the probability of your of the correctness of your conclusion. If you conclude that the process is still at this level, okay, what is the probability of making correct decision? If the probability that the probability of the points to vary within the control limits, okay, is 99.73%. Okay, again, if the mean is at this level, okay, the probability of seeing the points within the control limits is 99.3%, right? That means the probability of the points out of the control limit is 0.27%. Okay, so if you conclude that, okay, the mean is at this level, at this same level, okay, can you conclude it correctly? Can you make correct conclusion?
I think yes.
Yes, right. That is the correct answer. But what is the probability of making correct conclusion?
Is it 99.73?
No. Okay. I'm talking about that if you see the point, okay, out of the control limits, okay. Do you still, if the mean is at this level, okay, do you still have a chance to see the point out of the control limits? The chance that you see the point within the control limit is 99.73%, right? Okay, so the probability of you see the point out of the control limits will be 100% minus 99.73. Is that right?
Yes.
Yeah, which is 0.27%, which is very small, right? Okay.
Yes.
So that means it's unbelievable, okay, that because this chance is pretty small, okay, so you tend not to believe that if you see an X bar out of the control limits, okay, you should not believe anymore, okay, that the process is still at this, the mean is still at this level, because you have really few chance to see this point, given that the mean is at this level, right? But it's more likely that the mean of the process shift up, okay, to some certain value, for example, at this value, right? That makes the probability of observing this X bar, okay, the X bar at this point, more likely or with higher probability, right? So that means if you see the point out of the control limits, okay, like at this level or this level, you will not believe that the mean is at this level anymore, but you tend to believe that the mean shift up, okay, because there is higher chance to see X bar at this level, given that the mean shift up from its normal level, right? Okay, do you follow that? Okay.
Yes.
Okay. Okay. So if you understand this point, okay. So now let's move to the calculation. Okay. So UCL, okay, is set up at the mean and plus Z times sigma, which cover, okay, this range cover 99.73%. Okay. And then this slide show you the derivation, okay, to the formula that we will actually use for calculating control limits based on the raw data. Okay, so starting from this thing, okay, and take a look at sigma of x bar. Sigma of x bar is equal to sigma x divided by square root n with the central limit theorem. Okay, and then you take 1 divided by square root n out, right? And sigma of x, actually we have this formula to calculate sigma of x. Okay, sigma of x is equal to r bar divided by 2. Okay, you will see what does it mean by r bar and d2 in a minute from now. Okay, and then if this is sigma of sigma of x, right? Okay, and then if you group this constant, okay, to a new parameter which is called a2, okay? So you can get this formula, okay, because this is mu of x bar, okay, is equal to what we call x bar bar, and then, okay, we will have a2 and times r bar here, okay, and this is the formula to calculate the upper control limits, okay. Now let's take a look at the raw data and then the link between, okay, the data and the formula, okay. Okay, via this example, okay, so when we construct the control charts, first we have to define the process and quality characteristics we want to control. For example, we want to monitor the turning process, and the quality characteristics is the diameter of the turn part. Or if you cut, you have the cutting process, your quality characteristic is the length of the parts, okay. And the next step is to determine the sampling plan. In this case, mean two things: the sampling frequency and sample size. For example, you determine that you will have, you will do sample every hour. So 1 hour is your sampling frequency. And for each hour, if you design that you will collect 5 data points, okay, or 5 parts, so 5 is your sample size. Okay, and these two things depends on the stability of the process. If your process is not stable or instability so your sampling frequency should be at least 1 hour, okay. But if the abnormality happens, okay, every week, so you may not need to sampling every hour, it's too often, okay. You can sampling, for example, every day, okay. And nature of the process, okay, means okay, I'll talk about that later. Okay, nature of process may be, for example, your process make chemicals, and the nature is that chemical is homogeneous. Okay, so if you monitor this viscosity of the chemicals that you produce in batch mean, like, you know, batch like ถังผสม, okay. So for every batch, okay, you can take sample, like only one sample or one time or one measurement, because the viscosity in one batch is homogeneous, so you can have, you will have only one number for that batch, okay. So the nature of process, if it's homogeneous, so that's mean you would take sample like one measurement or per batch or per time. In this case, our sample size will be equal to 1, okay, because one measurement mean sample size equal to 1. But if your nature of the process is like you have turning process, okay, so, or cutting process, you cut the parts like a lot each hour, you cut like 100 parts per hour, okay, and for each part you can have different length, right? Okay, so if there is a variation among the parts during each hour, okay, in that case you should collect more than one parts, okay, to be a representative of the whole of all the parts you produce during that hour. Okay, so in this case, okay, you should use sample size greater than 1, okay. And how much sample size you use, like 10 parts per hour or 5 parts per hour, it depends on the production rate. Okay, so if your production rate is high, so you should collect more, okay. If your production rate is low, you should collect like 5 parts instead of 10 parts, for example. And you should consider the cost for the sampling and testing, okay. If your measurement or testing equipment is expensive, okay, you cannot buy a lot of equipment, so you need to sample less. Okay, that means you should use like lengthen frequency, or you should use smaller sample size. Okay, it depends on the limitation, okay, for the budget, okay, or the cost of sampling also. And also it related to the time, the testing time. For some equipment, for example, if you monitor the roughness of the parts, it takes like 20 minutes to measure one part. Okay. But if you monitor the length of the part, you can use the vernier to measure it. It takes just like a few seconds to get the measurements. So if your testing time, okay, is very small, okay, you can consider using higher sample size. Okay, but because higher sample size mean higher quality or higher chance to detect abnormality, right? Okay, but you have to trade off between the quality, okay, or the performance of your detection and the cost and the time that you have to spend on collecting the data. And when you consider, okay, all this thing, okay, you can start collect the data, okay, and the rule of thumb is to collect at least 25 subgroups of data. Okay, for example, if you need to you collect the data every hour, so you have to wait for 25 hours, and then you will get the raw data, which looks like this. Okay, in this case, they have 35 subgroups. Okay, we need at least 25, right? And then they decide to use sample size of 5, so we have 5 data points, okay, for each sample. Okay, and the next step to calculate the control limit is to calculate 2 statistics. The first one is X bar, which represent the mean of the process, and the next one is the range, or for S chart we can calculate S, okay, S standard deviation for each subgroup to represent the sigma of variation within the subgroups. Okay. For example, if you take a look at sample 1, the maximum is 2.7 and the minimum is 207 and 202. So the difference is 5 units. 5 units, right? This is the range. Okay. But if you use this 5 data points and you calculate the standard deviation instead, remember that, okay? X bar is equal to 204.6. Okay, if you calculate S using this formula, like the first one, X, remember this, Xi minus X bar square divided by 2 minus 1. Okay. If you calculate S, for example, using this formula, you will get like 205 subtract by X bar, which is this number 204.6, and then square, and then plus now 202 minus 204.6 square, right? And then you do this until again the last data point, which is 207. Right, square, and then you divide all this thing by n minus 1, which is 5 data points minus 1, and don't forget to take the square roots. Okay, you will get another, if I make another column, which is s, you will get another number, which is s. Okay, right, this. Okay, so the within subgroup variation, you have 2 choices of statistic to represent the within subgroup variation. The first one is the range, which is easy to calculate, okay? But the second one is standard deviation. Standard deviation has good point because it uses all data points right? 5 data points to calculate the S value. But for the range, it used only 2 numbers, right? Only the maximum and the minimum one, okay? So the number in the middle range, do not use it in the calculation. So if your sample size is high, for example, your sample size is greater than 10, that means when you use the range, it will use only 2 data points out of 10 data points. Okay, it neglects 8 data points out of the calculation. So when you're in the case that your sample size is greater than 10, sample size is greater than 10, you should use S chart instead of R charts. Okay, but if your sample size is between 2 and actually you can say greater than 2, okay, no upper limits, you can use I'm sorry, if n is from 2 to 10, right, you can use R or S chart. Either one of them is fine, because we can say that, you know, if smaller sample size, okay, less than 10, range is okay, it's enough, okay, it's okay to represent the sigma, okay, but if your sample size is greater than 10, range is not okay because it neglects too many data points. And then use only S chart, okay. But I would like to mention that in the case that you have small sample size, if you in nowadays when we plot the control charts, okay, we use computer program, right? So you don't need to do manual calculation anymore. So if you use computer program, okay, calculating S and R is not that much difference in terms of the calculation effort. Okay, so I recommend that you use S chart in all situations. When you have small sample size, you should use S. Larger sample size, you should S anyway, because S use all data points in the calculation. Okay, so R chart is used in like in the past, like several, like 40, 50 years ago, that okay, computer, there's no, you know, computer is very slow, okay, and it's pretty hard to do the calculation. Okay, they use that manual calculation, so they use range because it's easier to calculate. But nowadays, okay, we will use computer, and then we use S because it's better in terms of the quality of the information. Okay, next thing that you need to know, okay, about this, okay, is X bar. Okay, X bar is an average of all samples Okay, so it represents the process, the mean of the whole process. Okay, and R bar or S bar, okay, represent an average of the within subgroup variation, right? So each R tells you the within subgroup variation. 6 tells you the variation among the second hour. Okay, 7 tells you the variation within hour 35, but this variation is still within 1 hour variation, right? Because it is calculated from the max and the minimum of the 5 data points within the same hour, within 1 hour. So if we have 35 values and then we take an average, okay, we will get 7.5. So 7.5 shows you the variation within 1 hour anyway, but it's just an average, okay. Okay, And now we can calculate the control limits. Okay, so center line is at x bar. UCL and LCL is at x bar plus and minus constant A2 times R bar. Okay, so we you know now that how do we get x bar and R bar, right? And next is A2. A2 is a constant, which is you can look up from a table. Okay, in any QC book has this table. Okay, your sample size is equal to 5, right? So your A2 is 0.577. Okay, so you can plug in this number. Actually, you should 0.577 here. Do not round up. Okay, you should plug in the number which has significance like up to 3 digits from the table. And then you will get the control limits, okay? And then you can plot what we call the trial control limits, okay? We plot the control limit from the calculation, okay? And plot the x bar for each subgroup, okay, into the chart. Same thing for our charts, okay? For our charts, we have this formula to calculate, okay? Upper control limit is at D4 times R bar, LCL is at D3 times R bar. D4 and D3 you can look up from the same table, okay? And you can make this observation that when n is from 2 to 5, D3 will be 0. If D3 means is 0, lower control limit, which is D3 times R bar, will be 0 also, okay? Okay, now you get this thing, okay? And you plot all the points, right? Okay, and then you will detect 2 points that are out of control. Okay, what you need to do is that you have to think about this. Why? What happened? What is possible? Okay, that make the variation within this subgroup and this subgroup to like higher than its normal level. Okay, and then you should take a look at the raw data. For example, you come back and take a look at the raw data. For example, the abnormality happened within this hour, so you have to look at them. For example, the maximum one may be like 208, and then if you compare, okay, to other observations, you will see that this one is abnormally high. That makes the range, okay, very high, which is, for example, 12, okay? And then you see this point as out of control point, okay? So, and then you have to find out why this part has that like very high dimension, and then you will, the first cause that you have to investigate is to check whether it's a typo. For example, actually it's not 208, it's 198, for example. Okay, it's a typo. Or if it's not a typo, it's come from real abnormality. So you have to find out the cause of that abnormality and then fix it. For example, machine is broken, people or operator making wrong adjustments, for example, things like that. Okay, and then when you know the cause of the problem, you prevent it, okay, you correct it and prevent it in the future, right? And then, okay, what you need to do next is that you should delete this 2 points from the calculation of the control charts, because control charts should, the control limit should be calculated from this concept that all the data points that we use for calculating the control limit should come from the in control situation, okay? Because we will control limits is based on the concept that if nothing happened, nothing abnormal happened, the points should be vary within this range, okay, within this range. So this range should come from the point that normal. So if we see, for example, operator error, okay, machine broken, this thing is abnormal, so we shouldn't allow, okay, this point into the calculation of the control limits. Okay, so that means you need to find out the cause of the problem, and then you delete, okay, or remove, okay, those samples out. Now, okay, from 35 subgroup, now you have only 33 subgroups, okay, and then you recalculate the control limits, okay, and then you plot it again. And now you will see that with the new control limit, okay, the R chart is in control. Those 2 points that are very high is they were deleted, okay, from the calculation. And now you will have an update control limits for an X bar chart, okay, and then you will see that when you're, okay, because UCL is equal to X bar plus A2 times R bar, right? Okay, when your R bar is reduced, okay, that means you will get lower UCL, right? Previously, your UCL may be at this point, at the first round, okay, that is called trial control limit, is at this level, right? But when your R bar is lower, your UCL is lower, okay, up to this level. And now you will see that these 2 points now become out of control limits compared to the first round, that these 2 points, okay, are still within the control limits, right? But at the second round, in the second round, these 2 points now becomes out of control limits. Okay, and again, you have to investigate the cause of these 2 points, and then when you find out the cause, and then you can make can find corrective action, okay, to prevent it from happening in the future. So you can delete these 2 points again, okay, because it's abnormal. And then you redo, okay, the third round of the control charts, okay, and then now we will see that all the points are within the control limits, okay. So that means we get the final control limit that we can use it to monitor the process in the future, okay. And these are the steps that you need to do to get the final control limits. Okay, you start with the trial control limit from the first round, okay, and then delete, looking at the R chart first, okay. If you have S chart, you should take a look at S chart first, okay, and then delete the points of R or S chart first, and then you go to, actually I have this roadmap to tell you, okay, to help you, right? Look at R chart first. If R chart is in control, okay, take a look at X bar charts. If X bar chart is in control, you get the complete or final control limits. But if R chart is not in control, okay, you have to investigate and redo and revise the control limits here, mean delete the abnormal points, okay, and then you consider X bar chart in the next step, okay. And if it's still within the control limits, again, you delete the points until you get the final control limits, okay. Okay, in a few minutes, we'll have a break, okay. But before that, let's take a look at this thing first, okay. When you use control charts, you have to set up what we call out of control, okay, out of control action plan. That means the plan that will tell you the action when you observe an out of control situation. For example, if you see points out of control, first you have to check whether the data is entered correctly, okay. If yes, okay, take a look at that. If it's abnormal on X bar charts or R charts, okay. If abnormality happens, this is a specific okay, case for some factory. Okay, in this factory, they say that, okay, if abnormality happen on our charts, let's tell process engineer to fix it. Okay, but if something happen, okay, with an average, okay, so they think that there should be something wrong with the setting of the machine. So the first step that they think should be considered, okay, at the first step is to check the temperature and the time, okay, because they think that the abnormality is very likely that caused by temperature and time. So they should investigate these two factors, okay, as priority, right? Okay, if there's nothing wrong with the temperature, okay, if the temperature and time are not set correctly, right, they say that we should reset the temperature and time, okay, but if it's set correctly, so they move to investigating other causes, like for example hot plate calibration. Okay, if this is not if it's the cause of the problem, so contact the process engineer to fix it. Okay, so if it's not, let's move to checking other factors. Okay, so OCAP is like a flow chart to tell you what you should investigate first, okay, second, third, okay. And when you use the control chart, it's very important that you should record all information about the process. Information here mean any changes you made to the process. For example, machine adjustment, okay, the worker, if you change from worker A to worker B, so you have to make a note that at 9 o'clock, operator B, okay, come to work in the process, substitute the worker A, for example. So if there is something wrong, okay, after 9 o'clock, so you will know that they may be caused by an operator. Okay, record the batch of the raw materials, okay, the lot of the material and operator. Okay. Okay, after the break, okay, we will talk about the use or interpreting the pattern that occur on the control charts. Okay, so let's take a like 10 minutes break. Okay, is that okay? Let's take 10 minutes break and then we come back. Okay, and then let's download the file from CourseWheel, right? The file which has control chart data. Okay, and for the one that can that have download Minitab software, okay, you can practice using Minitab. Okay, but if you have some limitation with downloading software, okay, PMI can give you an output, okay, for doing workshop. Okay, so okay, let's take a break, okay, and then come back in 10 minutes. Okay, everyone. Let's come back to the class. Okay. I think I will change the plan just a little bit. So I want to switch, okay, to do workshop in the next class instead, because we need maybe more than 1 hour to do the workshop. Okay, so and because now we have 45 minutes left. Okay, so I will spend the remaining of the class today to talk about the lecture, okay, about other types of control charts, like the construction or the control limits calculation from other types of control charts. And then when we know, okay, all theory about this, and then in the next class we'll practice on using the control charts. Okay, so for the section which is about using or interpreting the control charts, we have like 8 tests or rules for detect abnormality that happen on the control charts. Okay, I will leave this to the next class. Okay, when we do the workshops, okay, we will practice on using this 8 tests. Okay, so let's skip this test, okay, for today, and then let's move to this slide. Okay, you have seen the calculation of the control limits for the X bar and R charts, right? Okay, and now for variable control charts, we still have 2 other charts left, X bar and S and XMR. Okay, and for control charts for multiple stream processing and for high capability process, okay, it's the charts that are used with variable data also, but it's not in the scope of this course. Okay, for X bar and S, actually it's pretty easy if you understand X bar and R charts. Okay, like in the case when your N or sample size is greater than 10, okay, as I told you previously that estimating sigma with R bar is not accurate. So let's use S instead of R, okay. And for the S charts, we have the formula, which is very similar to the formula for R charts. Okay, if for our charts, UCL is equal to D4 times R bar, right? But for S chart, D4 change to B4 and D R bar change to S bar. Okay, that's it. Okay, LCL we have B3 S bar instead of D3 S R bar. Okay, and S, okay, I have shown you previously about the calculation for each S, right? HI here mean the index for each subgroup. Okay, for example, SI is the standard deviation that you calculate from all the data points, all the 5 data points, okay, in each subgroup. Okay, in this case we have sample size of 5. Okay, and then if you have 33 subgroups, you will have S1, S2 until S35, right? If you okay, sum it and divide it by 33, you will get an average of S, right? This is called S bar. Okay. M here is the number of samples taken. In this case, it's 35 subgroups. Okay. Okay, this is the comparison of the formula for, okay, X bar and S and X bar and R charts. Okay. And one thing that you need to know is that we have statistics that we can use to express the variation of the data, right? The first one is S bar, okay? But S bar is not a statistic, which is called sigma. Sigma is standard deviation, shows variation like S bar, but it has some relationship. Okay, so you have to divide S bar with a constant C4. C4 depends on n sample size also. And then you can look up from a table. I'm sorry. A table also. So in S chart table, you have n sample size 2, 3, 4 like this. And then you have a constant A3 for X bar charts, B3 and B4 for S charts, and also C4 for calculating sigma. Okay. And interpretation of the charts, we will talk about this in the next class. Okay, we will use the same rule or test like as we have used for X bar in our charts. Okay, now let's take a look at an example of the calculation. So in this case, they have 25 subgroups. Okay, sample size equal to 1, 2, 3, 4, 5, and equal to 5, right? And for each subgroup, we calculate X bar and S, okay? And then we average all X bar, we've got X bar here, and average all XS, we've got S bar, okay? And then is enough for calculating the control limits. Oh, I'm sorry. Okay, why there's no, sorry. Let's take a look why there's no calculation. Okay, I'm sorry about this. There is no calculation to show you, but okay, keep in mind that after you've got X bar, right, you can calculate X UCL of X bar chart with X bar plus a constant A3. You can look up from a table and then times S bar. Okay, just plug in the number, which is very easy. Okay. Now let's move to the next control chart, the next type, which is IMR, or we can call I as X. Okay. For individual measurements, okay, these charts are used in the situation where we collect only one data point per time. Okay, it's used in the case where the production rate is very slow. Okay, so you can wait for many parts to come out. Okay, you cannot wait for 5 parts to come out, because each part may take, for example, 1 hour to produce. If you need sample size of 5, you have to wait for 5 hours. Okay, and it's too long. Okay, to give feedback about the process. So in this case, you can when you have 1 parts coming out, you can plot it right away. Okay, or you have the situation of the chemical process, okay, that you have like homogeneous substance chemicals. So if you measure, for example, the viscosity of the chemicals like 3 times within the same batch, okay, the variation or the difference among the data may come from like analysis error, or not analysis, to be easier to understand is measurement errors. Okay, so if the chemical is homogeneous, so you can sample only 1 time. Okay, but before that you have to do what we call measurement system analysis to make sure that your measurement system is correct. Okay, or you have an automated inspection. Okay, and then you can measure all the parts that coming out of your process. Okay, so you have all the data for all the parts. Okay, you can plot it. Okay, for every part that you produce. Okay, and this is an example of a chemical process. It's a paint. Okay, maybe on automotive. Okay, and then you monitor viscosity. Okay, and there are 20 batches collected here, but actually you should remember that you should, when you construct control chart, you have to have at least 25 subgroups. Okay, so in this case you should collect 5 more batches. Okay, but assume that okay, we have enough data points. Okay, so for each batch we measure the viscosity for each batch, and we have the data in this column. Okay, so if you take a look at the variation, let's take a look at this first. Batch number 1 viscosity is at 34.05. Okay, in the next batch the viscosity increased from 0.05 to 0.4. Okay, in the third batch viscosity reduced, right, to this number. Okay, so the first chart that you can make or construct is what we call X chart, or the viscosity chart for each subgroup. Okay, so you can plot batch 1, batch 2, batch 3, batch 4, and then you will plot the viscosity for each batch. Sorry, this is called X chart. Okay, but since for each subgroup we have only one data point, so we cannot calculate the variation among each batch within the batch, right? Because we have only one number. Okay, but you will see that there is variation between the batches. Like batch number 2 is okay, viscosity is higher than that of batch 1. Okay, so if you want to quantify the variation of the viscosity among the batches that you produce, so you can calculate another statistic which is called moving range. So you know that range is the difference, right? So the first moving range 0.35 is an absolute value, or mean you just take a look at the size, right, between X viscosity of batch 2 and batch 1. So this comes from 34.4 minus 34.05, okay, which is 0.35. Okay, the next you move, okay, the calculation of the range to this number. So 0.81 is the difference between x3 and x2, okay, which is 33.59 subtract by 34.40. Okay, and actually if you take a look at this, it has the negative number, right? But we take the absolute value. Okay, so we consider only the size of the difference, which is 0.81. Okay, and then you move, okay, rolling the calculation. Okay, so the last number here is the difference between X, okay, viscosity of batch 20 and 19. Okay, and now let's take a look at the meaning of this. So each moving range, each one of them tells you the difference of the viscosity among the 2 consecutive batches. Is that right? The difference between only 2 batches, the 2 consecutive batches. Okay, but since we have 19, okay, 19 moving range, if we, okay, average all moving range, okay, we will get the number which is called MR bar. Okay, so this MR bar of 0.57, okay, 0.57, okay, shows you that on average, because this is an average, right? So you can say that on average, the viscosity of two consecutive batches differ by this much, which is 0.57 whichever units, okay, you can say. Okay, but X bar, okay, tells you different thing. X bar tells you that on average, okay, this is the viscosity of the paint is 34.088. Okay, this is an average, okay, of the viscosity, but MR bar shows you the average of the difference between the viscosity of the two batches. Okay, and now we can plot the control charts. Okay, okay, first the control limits of the X chart first, okay, is at mean, which is X bar, right? And plus and minus 3 sigma, okay? Remember that. Sigma for X chart is equal to this, okay? So when you get MR bar and then you look up a table, okay, which to look up a D2 number, it depends on N, sample size. And in this case, okay, in this case, sample size in this case is not 1. If you take a look at this table, for each batch, you have only one data point, right? One data point. But the sample size for calculating D2, okay, is not 1 because we have to consider it like this, okay. D2 actually is a constant to convert MR to sigma, right? Okay, so that means when you've determined the sample size in this case, you have to think about it like this. You have to think that for each MR bar, okay, how many data points that you need to consider, okay, when you calculate each MR value. So if you take a look, okay, at the table here, each MR like 0.35 here, you consider this two number, right? Okay, to come up with this data point. 0.81, okay, you consider these two data points, right? So that means for each MR value, you consider two consecutive numbers. So in this case, 2, which is the data point that you consider, is the sample size in this case, okay, the sample size for calculating the D2 number, okay. So in this case, you have to look up the D2 number from the table, sorry, using n equal to 2, okay. And okay, you will have D2 here. Okay, you've got MR bar and X bar from the table. Okay, and then for control limits for the moving range chart is use the same constant as R charts. Okay, for LCL is equal to 0 because it's D3 times MR bar, right? But remember that D3 when n equal to 2 is equal to 0. I'm sorry, this is D3 is equal to 0. So it will make this thing equal to 0. Okay, so this is the formula for calculating X and MR charts. Okay, after you do the first round, or what we call trial control limits, okay, you plot it, okay, and when you do interpretation, okay, the rule is that because moving range, okay, it depends, right, on X, the X number, right, okay, so that's mean moving range is dependent on X chart, like in this case, moving range like number 3 is very high. It's because the difference between X X4 and X3 is very high. Is that right? That means this one is high because this number is high. Okay, so to detect abnormality, so we people agree that we will use only X chart, okay, to detect the abnormality. Okay, so you don't have to take a look at MR charts, okay, when you detect the when you judge about the abnormality, but you can use it, okay, in conjunction with X, okay, to tell where the difference happened, okay. But when you say that the point is out of control or not, you should make your decision based on X charts, because sometimes it's possible that it's out of control in X chart, but for the R charts, it's near the control limits, okay, but it's not beyond the control limit. So you have to use only one chart to make the interpretation, that is X chart. Okay, and then, okay, you revise it, okay, delete this, okay, and you will get the new set of control chart, okay. And next you can, after you get the final control limits, you can collect the data more, okay, and then you will use, okay, the control limits that you have calculated to monitor the part, okay, or the batches in this case in the future. Okay, so first you have 20 subgroups, right? This is the periods of construct the control chart, okay, and the output is control, actually our control limits, okay. And after this goes to the period of using the control charts. That means you don't have to calculate the control limit anymore. You don't have to update it all the time, because it involves a calculation all the time. So you can fix the control limits, okay, at the level that you have calculated, and then you just plot, okay, the new data onto the control limits that you have, and then make the interpretation whether the process is out of control or not at each hour that you collect the data. Okay. About interpretation, we'll talk about this in the next class. Okay. But remember that we use this concept, okay, right, to calculate control limits, okay. And with this concept, we assume that, okay, X is normal, has normal distribution, right? Okay. But if okay, normal assumption is not met, okay, we cannot use this formula. That means we cannot use XMR chart, okay. We have to move to some like other complex chart, which is QCM or EWMA, okay, because these two types of charts are less sensitive, okay, to the normal assumption. Okay. Okay, so we finished, okay, the section about the construction, or how to calculate the control limits of 3 types of charts, right? We have seen X bar R, X bar S, and XMR. Okay, XMR or IMR. Okay, we have done that. Okay, now we will move to the control chart for attributes. We have 4 charts in this group. Okay. Okay, remember that from last time we, okay, distinguish or find out the relationship between 2 words, defects and defective. Okay, revisit it. Okay, briefly, defect is the thing that we do not want on the part, okay? And for one part, it can contain more than one defect. For example, 1, 2, 3. Okay, 1 here, 1 here, 1, 2 here. Okay, and the part that contains at least one defect is called a defective. Okay, or rejected part. So this one is a defective. This one is a defective. This one is a defective. This is a non-defective, right? And we will see that for each part, okay, the data that we collect, okay, can be classified in terms of the category, right? For example, part number 1, okay, the result, okay, from the measurement will be, or the inspection will be a type which is called defect. It's a defect, or it is a defective. Part number 2 is a defective. Part number 3, defective. 4, defective. Number 5, no defective, like no defect, it's not defective. Part number 6, defective. 7, it's not a defective, right? So we will see that the data, our data is attribute data because it comes in terms of in the form of category of defective or non-defective, right? But next, we have to turn this data into some indicator which is meaningful. And the indicator which is meaningful is, okay, the first thing is what we call fraction defective or defective rate. Like in this case, there are 10 parts that we sample, and there are 6 parts that are defective. So the proportion is 0.6, okay? This is what we call P, okay? We will use the notation P to represent the proportion of defective, okay? Okay, sorry, just a second. And the more things that we need to know is that suppose we produce, okay, the parts, okay, many hours, okay, for example, from 8 to 9 o'clock, we want to know or monitor the proportion of defective during 8 to 9. And from 9 to 10, we also want to monitor the proportion of defective also. And we want to monitor about the proportion of defective for each hour that we do production, right? So we can make the chart which is called P chart, like in this example. This example, we produce can, for example, think about food can, okay? Maybe like pineapple in here. Okay, or in automotive, okay, you have like you weld, okay, do welding, okay, to join 2 parts, and then you want to collect, okay, the proportion of parts that have welding error, okay, things like that. Okay, in this case, the can has defect, which is this the leak, okay, on the side seam of the can, okay. So they want to monitor the proportion of defective, so they collect 30 samples, and for each samples mean 50 cans, okay, and then they inspect 50 cans per hour, okay, in this case, actually for every half an hour in this case, okay. And then this is, okay, the table that shows you the data, okay, for first sample, which is 50 cans, okay, there are 12 cans that are defective. So if you convert, okay, this into a proportion, it will be 0.24, Okay, and then you do this for all the subgroups, right? For each subgroup, you have the same sample size. So in this case, sample size is constant for all subgroups, which is the same. Okay, it's at 50 cans. Okay, so after that, okay, you get proportion, right? For 16, 17, 30 subgroups. Okay, and if you calculate an average of the proportion over 30 subgroups, you will get what we call P bar. Okay, an average of the proportion. Okay, and then now you can start to calculate the control limits, because the formula is like this. P bar represent the mean, right, of the proportion. Okay, 3 is C score, right? And then this is sigma for P. Okay, sigma of the proportion has this formula. Okay, you can plug in this formula here. This is sigma, right? And sigma of proportion data is P times 1 minus P divided by N. Okay, and actually P here is the population proportion. That means the proportion of the defective cans of like the population. That means if you produce this for days and days, okay, you do not know when we're gonna end this production line, right? It's a population. But in this case, we do not have the data from the whole population. But the best that we have is P bar, right? Which is the average of the proportion over 30 subgroups that we have. Okay, so we will use P bar instead of P, okay, to represent the population. Then we will get this formula to calculate UCL. Center line is at P bar. LCL, okay, is okay, just change from plus to minus, right? Okay, N is equal to 50. Okay. Okay, and this is just show you the link, okay, between you don't have to pay attention to this, okay, just want to tell you that actually P proportion is equal to the number of defective parts divided by N, right? And D, the number of defective part, actually D here has the distribution which is binomial. Okay, binomial, and binomial distribution has this much, has this what we call PMF, or probability mass function, that shows you the formula to calculate the probability of seeing its x value. And for a normal distribution, the mean, okay, is equal to N times P, okay, and variance is equal to this formula. And then we can derive using this formula to come up with sigma of the proportion. Okay, you can take a look at this. Okay, take a look at this by yourself. Okay. Okay, now let's move to the next piece of information. Okay, so control limit is set up at this level, right? And since we know that the proportion comes from the number of defective, and defective has binomial distribution, okay, but this formula that we use to calculate the control limits is based on normal distribution, right? That means we have to, and we know that binomial distribution can be approximate with a normal distribution if these two conditions are true. But why do we have to link between binomial and normal distribution? Okay, that is because the control limit is based, we assume normal distribution to calculate the control limits. Okay, so normal assumption has to be true. But okay, the initial distribution, okay, for calculating P is D, and D has binomial distribution. Okay, so that's mean if we use the normal distribution to calculate control limits, D also has to be normally distributed. So for some parameter, it can has two distribution at the same time. D can has binomial distribution and also has normal distribution at the same time. But only for some conditions, okay, that should be true. Okay, the first condition that make binomial distribution be normal distribution is that the sample size has to be at least 30. Like in this case, your sample size is 50. Okay, you collect 50 cans per subgroups, so it greater than 30. Okay, so your first assumption is true. The next condition is this. When you calculate p bar, in this case it's 0.2313. Sorry, it's 0.2313, right? This is called p bar. And if you multiply this by n, 50 in this case, okay, is equal to about maybe 13, I'm sorry, 10. It's about 10, right? Okay. If 10 is greater than 5, okay, that means this condition, okay, we pass this condition. And also the third condition has to be true. That is 50 times 1.23. Okay, it's 50 times 0.8, 0.67, right? Which is about 30 something. 30 is greater than 5 anyway. Okay, so that means we pass this condition also. Okay, so if the three conditions, okay, are met, so that means we can approximate, okay, binomial with normal distribution, and then we can use this formula, okay, to calculate the control limits. The calculation that you have seen so far. Okay, so to summarize about this, to use this formula to calculate the control limits, first you have to check these three assumptions, okay, these three conditions. If they are true, you can use this formula. If they are not true, you have to use some other control chart, which is QSUM or EWMA. We cannot use a ordinary P chart, but we have to use QSUM P or EWMA or P chart instead. Okay. Okay, so this is just to show you how to plug in the data, right? And then 2 points of control limits. Okay, you investigate, okay, the cause, prevent it, and then delete it, right? And now, okay, you've get, and then you revise it until all the points are within control limits, okay? And okay, they delete this point, this point, this point. So this control limits actually come from only 22 subgroups that they have deleted these 3 subgroups already. Okay, and these lines want to show you that if you, okay, first you get this set of control limits, right? But at some point, for example, you do machine adjustments to improve your process to have less proportion of defective. Like in this case, your proportion of defective P bar is at this level. It's not at this level anymore. It decreased, right? So at that point, you should revise your control limit. Okay. You do not want to use the same control limit anymore because your center has changed already. Okay. So you have to update your control limits. Okay. Every time your mean is updated. Okay, interpretation of p-chart, we will visit this, okay, in the next class. There are 4 tests, right? But you can use, there are total 8 tests that you can use, but for p-chart, we will use only 4 tests, okay. Okay, and in the previous case, we see the case where our sample size is constant. That means every subgroup used, we have the same number of parts, okay, that we sample. But in the case that we do 100% inspection, okay, for example, we do garment industry, and for each hour mean each subgroup, okay, we produce different number of shirts, okay. For example, in the first hour, we produce 100 shirts, okay. Or in automotive industry, you can, in the painting process, for example, in the first hour, you paint 100 parts. In the second hour, you paint only 80 parts, okay. So it's sample size difference, okay, among subgroups, right? In this case is what we call the case of, we have non-constant subgroup, okay. So if you revisit, okay, suppose this is upper control limit and lower control limit, right? The control limit depends on n sample size. If sample size is 50, you will get, okay, different control limits from when n is equal to 60. Is that right? Okay, so that means the control limit depends on sample size. But if your sample size vary, so your control limit will vary, okay, also. Like in this case, okay, vary, so you get vary control limits. But if you get variable control limits, it's pretty hard to plot or to implement. That's because it means that when you have, for example, this subgroup, okay, so you have to calculate the control limit every time, okay, for each subgroup, and then you have to plot every hour, okay. You cannot have like a control limit which is constant like this, okay, that you can draw it in advance. So people come up with, okay, the second method, okay, to do p-chart. They want the control limits to be a constant, so that means we have to find out a constant sample size, right? Constant sample size. So they decided they will use n bar, average sample size, to calculate the control limits. So n bar is a constant now, okay, because it has only one number, right? So like in this data set, you average 180, 80, 81, 110. You average it, right? And then you will get n bar, which is equal to, like, in this case, see. Okay. For example, n bar is equal to 1.1, 101.5. So you plug in here, and then you will get, okay, constant UCL and LCL, right? Okay, this is, okay, calculate sample size, average of sample size, and then you will get control limit, which is constant. But when you use this type of control limit, you have to you have to pay attention to the points which is very close to the control limits, like this point, because this control limit, okay, come from n equal to, for example, this number. But the actual control limit of this point, suppose this is come from the subgroup of when n equal to, suppose n equal to 110. Okay, so we know that the actual control limit is based on the actual n, right? So when n, actually the actual n is larger than n bar, right? N bar. So the actual control limit will be smaller, okay, will be narrower, because the upper control limit is at p bar, plus, right? P bar times this, and then divided by n. So if n is equal to 110, it will make UCL lower than when n equal to a smaller number. Is that right? So that means when you do interpretation whether this number is out of control or not. If you make decision based on n bar, you would say that is in control, right? But at the actual control limit, you should say that this point is out of control. So this is true, this is wrong, okay? But if you use n bar, method of n bar, you will make wrong conclusion, that you will say that it's in control, but in reality it's out of control. So the concern for this method is that when you have the point which is near the control limits, you should not use control limit based on n bar, but you have to calculate the actual control limit of that point. Okay, but for the point that, okay, around the center line, you don't have to recalculate the control limits, because, okay, the it's not very sensitive, okay, because it's not near the control limit. Okay, same thing for when you have the control limit, which is the point which is extreme point. Okay, so you have to calculate the actual control limit of this point based on actual n, because it's possible that, okay, the actual control limit will be higher, right, when n is smaller, and then you can make wrong conclusion. If based on n bar, you will say that it's out, but actually it's in control. Okay, I'm sorry, we let's just have 2 more minutes and then we'll finish the course. Okay, let's wrap up with this section. The last method to calculate when we have variable sample size is that we will use what we call standardized control chart. So we will convert, let's take a look at this. We will convert the proportion into the standard normal variable. Okay, and if you remember, C is equal to actually x minus mu divided by sigma, right? In this case, your x is the proportion of each subgroup that you are considering. Mean is p bar, right? And the whole thing here is sigma of p, right? And then, okay, when you plot the control chart, your UCL and LCL will be 3 and minus 3. Remember that actually your UCL is like mu of p plus 3 sigma p, right? But in this case, we do not plot p anymore. We will turn p to z. So when we compare with the control limits, we have to compare in scale of z value, which is 3 and minus 3. And each point that we plot here is the C score, which is pi minus p bar divided by, okay, square root p bar times 1 minus p bar over n. N here, ni. We can plug in actual I in calculating z, okay? So the last method has advantage over the other 2 previous method in that each z value considered actual n. So, and we will have constant control limits that we want. Okay, so with this constant control limits, we do not have like disadvantage like in the method of constant sample size that we have to reconsider the actual control limit when we have the points very near control limits, right? Because the actual sample size has been considered already when we calculating z value. Okay, but the disadvantage of this method is that the z-score, okay, is pretty hard to understand, okay, from people that are not familiar with statistics. Okay, so if you plot proportion defective, your worker will understand what does it mean by proportion defective, but your workers may not. It's pretty like it's more difficult for your worker to understand what does it mean by z-score. Okay, so that is the disadvantage of this chart. Okay, but if you want to use it with the objective just to detect whether the abnormality happened, you can use it. You can use z-chart. Okay, with this and take the two advantage of the z-chart. Okay, the first one is the correct interpretation based on actual n and constant control limits. Okay, so we have done with the P chart, right? Next, in the next class, we will talk about other charts, which is N, P, C, and U, okay? And then we will do workshop, okay, of X bar and S chart, okay? And, okay, so in the next class, you can prepare mini tab, okay? For each group, prepare, okay, one person, download Minitab, okay, and the other 2 person you can wait because Minitab can use only 1 month, but now we have like maybe about 1.5 month, okay, to finish the course. Okay, so in the next month we need Minitab from another notebook, okay, to plot to help you construct and plot the charts. Okay. So far, do you have any questions about the material that we covered in this class? Okay, so if not, okay, let's meet in the next class. Okay, see you in the next class.
ขอบคุณครับอาจารย์
Okay, สวัสดีค่ะ
สวัสดีครับ
สวัสดีค่ะ